Wakeman. I work for Arvig. We're a rural telecommunications provider that started in the mid-50s and has continued on since then through a number of acquisitions in the state. My own personal experience in the telecommunications industry started about 15 years ago, actually, starting fixed wireless WISP, working for Electric in Melrose, Minnesota. We kind of covered Todd, Stearns, Polk, Lewis portions of those counties with the service platform. So that's kind of where I started, and then moved on into more traditional wireline services and network data center side. But when we talk about fixed wireless, Andy kind of touched on it a little bit. I'm really talking about a tower going to probably either a fixed CP that's mounted on a building or near a building, or maybe moving into a portable scenario, whereas the mobile industry, they look more at your handsets and things like that. As we're getting into 5G, we start talking about IoT, and some of those conversations we've had around that so far today, those lines are blurring a little bit when what's a mobile technology, a mobile service provider doing versus what's a fixed service provider doing. Diane asked me to come in and to kind of talk a little bit about some of the more technical details of propagation, performance, what can we expect. And really, there's no free lunch in this. So when a customer or a vendor comes in and says, our platform does this, it'll do this many megabit a second, it's got this kind of capacity, we start looking at a number of things. My engineering mind looks at this stuff. So it really comes down to these first two are linked, which is why I grouped them. So if you want performance, you need to have a strong signal going to that CPE, and that's what helps with efficiency. So if you're thinking in terms of human conversation, if you're in a crowded room with background noise, you have to speak more loudly to be able to be understood by the person you're talking to, get closer to them, those kinds of things. So that directly relates to an RF network too. I mean, voice propagates through the air in a lot of the same ways that RF propagates through the air. So you need to have that volume of voice above whatever the background noise is in order to be heard and understood. The other piece is kind of efficiency. So you can kind of think about this from the standpoint of, say you've got two people standing across the field. You're trying to talk to that person on the other side of the field. You can't talk as quickly as I am today. You can't embed as much information in the same block of time as you can if you're standing closer to them. So if you're shouting across the field, you're probably, hello, you're dragging that out versus having a conversation face to face. So those two factors really, fit together. Or if you think about it in the house, you're trying to yell at your spouse or your kid through all the walls in the house. I mean, it's the same thing. You've got something in a way that's attenuating your voice. They can't hear you as well. You have to speak more slowly, more clearly. The same things really apply to an RF network. The second one is kind of independent. So it's, how big is the channel? So when Andy was up here, he was talking about 100 megahertz of spectrum kind of across their footprint, across their portfolio. And, that's one way of looking at it. There's building blocks. So the wider the channel is, the more information you can pump through it at the same level of efficiency. So they kind of feed on each other. And this is a really gross simplification, but if you want some rules of thumb to kind of think about it as we compare some of these technologies, this 75 megabit of raw throughput in a 20 megahertz channel. That's kind of a basic building block at performance levels and efficiencies that are typically seen in a real world scenario today. So when Andy's here and he's talking about 5G, you're probably seeing better efficiency than this at short ranges, and we'll talk through that in some of these technologies. And if you're at longer distances, you're going to see poorer performance. So some of that comes down to network design. You don't want to design your wireless network, especially if you're focusing on fixed wireless, for the lowest common denominator, because you're going to bring the performance of your entire system down by attempting to serve all those outliers. So we'll run through a couple of these different frequency bands. You'll see this header at the top, unlicensed, licensed, lightly licensed. So some explanation in that. So an unlicensed band is essentially, you buy the equipment, you go use it. If you get interference, you have to accept it, and you're not supposed to interfere with anyone else. You don't have to register it, you don't have to buy it, you don't have to do anything like that. You just basically deploy equipment that uses that spectrum. When we say it does not cause or receive interference, we're talking about, in relationship to systems where you paid for that license. So like 700 megahertz spectrum, there was a huge auction a couple of years ago. Millimeter wave, there's been a number of auctions recently. So essentially someone paid for the privilege to have exclusive use of that spectrum. TV channels, right? So they're broadcasting on channel 4. CBS paid for that. They get exclusive use of that. You can't interfere with that. So 900 megahertz is kind of a traditional band that's been used. You get some non-line of sight penetration, but you can see this is kind of the average speed you might be able to provide to a CP. So the reasons for that is you're dealing with only 26 megahertz of total spectrum. There isn't very much, and if you have to try to coordinate it, usually when you deploy a tower, you've got either one sector or 3 sectors covering 120 degrees, or maybe 4, each covering 90, some kind of coordination like that. So you have to break that amount up and try to use it across each sector. So you get a couple miles, probably 1, 2, 3 miles if you're going through trees and things like that. That's really the reason this has been used historically. But due to the low amount of bandwidth that's really available, a lot of this is kind of shifting towards SCADA applications, or kind of that low bandwidth application, which I would think long term might shift more into that IoT, that LTE-M kind of play, where your cellular technology is able to. This is another band that's unlicensed that has been used historically. This is also used broadly for legacy Wi-Fi technology, so Wi-Fi 4, Wi-Fi 5, or the old version 802.11g and N. Again, it's not bad. It's purely line of sight, so you won't get through much in the way of foliage or trees. It's deployed in a rural environment. It's going to be, the receiver on the customer premise or near the customer premise has to be able to essentially, you can see it with your eyes, you can essentially deploy it line of sight. You get more throughput. You might get 50 to 100 megabit per second down, 10 to 20 megabit per second up. These throughput numbers, they vary a bit depending on vendor and platform, but I mean they're good kind of average numbers to think about. There's a lot of Wi-Fi interference, or has historically been, and really the reason that you see less of this is because you get the same kind of performance when you start to talk about 5 gigahertz, but there's a lot more spectrum to use. You have 100 megahertz here total, which really breaks down to usually about 3 20 megahertz channels, whereas in 5 gigahertz you have 1,000 megahertz to use. So you have a whole lot more spectrum to work with, so when somebody's working on developing a technology, this is more of a dead end than a 5 gigahertz product. If you've been watching the news for probably the last 5 years, you might have seen CPRS. The FCC released about 50 megahertz of 3.65 gigahertz spectrum about 10 years ago under, they called it a lightly licensed scheme. So you had to go online, basically say, this is where my transmitter is, this is the direction it's pointing, this is the transmit power, and you could essentially use it. It was purely for wireless ISPs. So that worked very well. You were supposed to coordinate with other service providers that are running the same spectrum in the same area. So starting about 5 years ago, there was a lot of conversation about revitalizing that and adding additional spectrum to that. So the FCC created 150 megahertz block, and it's been highly contentious ever since. The benefit being that you're starting to see more performance and more range in a non-line of sight scenario. Part of the complexity is that we finally, at the end of January, the FCC announced general deployments in this spectrum, but the roadblock has been that they deployed a whole back-end infrastructure. So every radio you deploy in a fixed scenario more or less has to talk to a back-end database and obtain permission to transmit. And that's because they're trying to protect the 2 primary incumbent users. So there's ground earth stations feeding satellites, and along the coasts, the Navy uses this spectrum for their radar on their various cabinet ships. So they're doing everything they can to protect those users and to coordinate this spectrum. Later this year, there's going to be an auction. You can pay for essentially exclusive use to a portion of this band. They're going to auction off 70 megahertz of the 150. But from a technology perspective, it's a good fit. The fixed wireless providers, you're getting more throughput. So you're talking about being able to offer kind of real world sector capacities of 100, 150 megabit a second. You get non-line of sight penetration. You can really deliver a 25 and 3 type service when you're talking about those Minnesota goals and objectives. You can really deliver that kind of service with a reasonable footprint in this technology. And the costs are potentially lower than some of the proprietary technologies because a lot of the development is to date with the new rules has been on LTE based equipment. So this is an example of where you're starting to employ as a smaller operator the same technology and the same back-end hardware that an AT&T or Verizon might.
Excuse me, Ben, you said 100, 150 speeds. You meant download speeds,
Yeah.
right? So what's that upload speed look like? Is it just 120?
LTE in and of itself is really heavily weighted to download versus uploads. You get kind of a 10 to 1 or 80-20 kind of split, and it doesn't go too much more beyond that, maybe 70-30. So that's kind of what you're looking at in this band too. We'll talk about some ways that they improve the efficiency, but yeah, it's not a symmetrical platform. It's always going to be an asymmetrical platform. It's just the way it's fundamentally designed, unless you're running more proprietary hardware. Latency is going to be a little higher. So we didn't talk about that much earlier, but anything between 10, 20, 30 milliseconds the customer doesn't typically notice from a broadband application or from an interactive application. That difference in latency, really what's typically been more important, unless you're a gamer or something like that, where you're really wanting that kind of twitch reaction time. Stability in that latency is much more critical. So 5 gigahertz has been and continues to be a very, very popular band for fixed wireless deployments. You'll get less range depending on, this range will vary because there's kind of 3 sets of rules for that 1000 megahertz of spectrum. And I'll show a slide that kind of shows a little bit of that. This is line of sight only again, so I mean, maybe if you're within the same community, you might go through a tree or two to get into your house, but it's really got to be line of sight to the tower. Talk about this in a minute, but you can achieve very high throughput. So if you're talking like Wi-Fi 5, Wi-Fi 6, you've seen some of those advertisements potentially with equipment that's running close to a gigabit a second. You can see real-world throughputs of some kind of performance like that. That's a lot more feasible to see something in the 50 to 100 megabit per second range. You could deliver a 100 by 20 service on a lot of these platforms. Do it pretty comfortably. When you talk about that symmetrical, there's a lot more proprietary hardware in this that uses this band, so you have a lot more flexibility in those systems to say configure a 50-50 split. So you can have as much upstream and downstream, or you can kind of tailor it to your network needs 70, 30, 60, 40. So you can get closer to that symmetrical type performance. The challenge is coordinating that in your network. So you have a lot of different cells. They typically need a pretty consistent and comparable configuration if they're using overlapping channels. Otherwise you create interference with your cell.
So one of the things you mentioned is line of sight. And about lanes of higher lanes out there, how many people think?
That's really technology dependent. We'll talk about that a little bit. I mean, historically it's been kind of me and you.
Yeah.
And that's changing. So we'll touch on that in a little bit. So this is why this band is more broadly deployed than 2.4 gigahertz. Because 2.4 you get about this much. Whereas you can see this is Wi-Fi channels, but realistically you can use these in fixed scenarios too. So your 20 megahertz channels, you've got quite a lot of them, or if you're really focusing, so when we start talking about that 500 megabit plus, you're running these 80 megahertz channels, most likely in the wild to get that kind of bandwidth. So that's where that channel width really comes in. The challenge is coordinating that. So historically this has been used, so when Andy mentioned wireless backhaul, this band has been used quite a bit in the past to provide point-to-point connection between cell towers, or not even in the cellular industry, just general users of the band have been out there. So there's a lot of noise in it. It's, you know, that volume of the background noise is really a challenge in this band, to try to find a clean channel or enough clean channels to run. Millimeter wave, so AT&T guys touched on this too. The benefits, it's really this 500 megabit per second symmetrical bandwidth. That's a big pipe. The challenge is that your real world deployments are a couple hundred feet, a couple thousand feet maybe. This 250 to 300 meters is really what everybody's saying today as, from a fixed perspective, the max distance. Now this is quite a range of bandwidth, or of spectrum, so we've had options in the 24 gigahertz, 28 gigahertz, there's some upcoming options for 37 gigahertz. There's some unlicensed and lightly licensed spectrum in the 60, 70, 80 gigahertz band. So it's a big chunk with lots of options in it, which is why it's been attractive to carriers and fixed wireless service providers. It can be really interesting. Rain can be a challenge, especially as you get into the 60, 70, 80 gigahertz solutions. You get a little more range in the 24, 28, 37. You might get a kilometer or 2 kilometers out of that. So you're getting a trade-off there. Facebook is really also driving some innovation in this band from a perspective of how the networks are built and how they communicate between nodes, largely to help address some of this range. So this is kind of one way of looking at more urban deployment of millimeter wave. The red is fiber backbone, and these green connections are millimeter wave links. So when you start looking at it, you can see it's short range. One play of fixed wireless has historically been as a disruptor, right? So if you were in here as the incumbent and you had this much fiber, you could deploy GDOT fast in these areas and get over a gig of speed. You could deploy a new DOCSIS node and get over a gigabit of speed to the customer. This is a really good option if you have fiber and you want to kind of disrupt the market. So this is what Facebook is helping to drive. You can see in here, you have nowhere near as much fiber. Your build costs are a lot lower, and they're driving really these protocols to get each of these radios to talk to each other and build a self-healing network. So if one drops offline and you can see other ones, you can bring the traffic around that, and you don't need this fiber infrastructure, this fiber backbone that was really expensive to build to get the connectivity to each of these sites. And that's really important when you start thinking about, here's a picture of small town Minnesota. This is a 300-meter circle. You probably never see this in the wild. This is best case. You probably see about half of that. So, you could cover the downtown area in a small community with 2 or 3 connections, especially if you could get fiber in and kind of have that self-healing network. This is an overlay of downtown St. Cloud, so you get those urban mountains and valleys, and they create their own challenges where you're really on that street furniture. And that's where this model, you can kind of see it's modeled out that way. You've got the taller buildings that are going to make it a lot harder to pick, one high spot and actually get reasonable coverage. This works well where you have, 1 or 2 high spots in kind of a business district, and the buildings are all maybe 1 or 2 stories high. Whereas you really have to probably see a deployment more like that in those urban scenarios. And kind of to the point of not an ideal rural technology, I just picked a random tower and dropped a 300-meter circle on it. You get 1 customer. So it doesn't work very well in that kind of scenario. You just don't have the range. TV white space. So roughly 10 years ago, as the broadcaster started going through a digital transformation, reducing transmit powers, the FCC said, got a lot of spectrum out there. As a coworker of mine used to say, these low frequencies come with a shovel built in. They'll go through hills, they'll go through trees, they really propagate. So they opened this up. So you can use this from an unlicensed perspective with the caveat that it cannot cause interference with the broadcasters. And that's essentially been the challenge. Spent a little bit of time last week kind of calling around to people that have used this. More hype than reality. There's a lot of potential here. There's a lot of people with Rise Broadband, something like 200,000 fixed wireless subscribers in the country. There's a provider in the Upper Peninsula of Michigan that's been running some demos on this. They've been doing it for years and they're on their 4th tower. There's been significant kind of technological challenges getting this to work. And a lot of it has to do with the fact that it does come with a shovel built in. So when they're trying to get it to get out there and use it and find clean spectrum, that's really been a challenge. They've been finding that broadcast TV channels leak outside of their assigned channels